The theory of relativity. In a minor league clubhouse in Florida, a shortstop turns to a second baseman and asks, "Is it true that time moves faster when you are moving than when you are still?" The second baseman turns his cap sideways and replies, "I don't know. Let's find out." The middle infielders then approach a pitcher and propose the same question. "Do you know the answer?" To both questions, the pitcher politely answers, "Yes." If you have a question about life in minor leagues, come to Clubhouse Questions. We discuss these things. Clubhouse Questions. Folks, welcome to the first, and very likely only, episode of Clubhouse Questions. Do enjoy, and please keep your hands to yourselves during the showing. A few years after the first World Series, which happened in 1903 and resulted in the Boston Americans besting the Pittsburgh Pirates 5-3, a nerdy young patent clerk in Switzerland was struggling with the same question as our shortstop from earlier. The clerk's name? Albert Einstein. A reject to professional science at the time, young Einstein solved this question on a bus of all places. Think about that the next time you're watching Netflix on the way to Palm Beach. While looking at a clock out the back window of the bus, Einstein wondered, what would happen to time if the bus were moving at the speed of light? Then it hit him like a fastball in the ribs. Time would stop. To understand why this is, let's first talk about relativity in a more classical sense. All people, animals, objects, everything in the universe exist in relation to one another. For an example of the classical relativity of speed, let's pretend we're on top of a bus in the middle of nowhere. Mason is throwing a flat ground on top of a bus to Jason, whose arm appears to be totally straight and normal looking. Jason then flips the ball back to him while JP watches. When all three of them are standing still, they each appear to each other not to be moving, so they are all moving 0 miles per hour, relative to each other. But relative to the policeman, sitting on the side of the road wondering what the heck they're all doing, they are each moving 50 miles per hour, which is the speed of the bus. Now, if Jason throws a 95 mile per hour fastball to Jason, and then JP tracks the speed on the stalker gun, JP will get a reading of 95 miles per hour, which is the speed Mason throws the ball. But the next cop on the road, who's wondering why the first cop didn't pull him over, also tracks the speed of the pitch on his radar gun and gets a reading of 145 miles per hour. See, it's 50 for the bus plus 95 for the pitch, both moving in the same direction. The baseball thus is moving 95 miles an hour and 145 miles per hour at the same moment in time, depending on who the ball is relative to JP or to the policeman. Obviously, this situation only applies so long as the bus constantly moves at 50 miles per hour in the same direction. If the bus were stopped, the 95 mile per hour pitch would appear 95 miles per hour to everybody who was stopped. To the cars on the other side of the highway traveling 50 miles per hour into the pitch, it would appear still to be 145 miles per hour. But to the scout who's clocking the pitch from another bus going 50 miles per hour away from Mason and Jason, who are both wearing their team hat bracelets unlike JP, Mason's pitch would now get clocked at only 45 miles per hour for the scout. Now let's speed this situation up to Einstein's level. A scientist named James Maxwell figured out a little before Einstein's time that light travels at the speed of 186,000 miles per second. That means that light moves 36 million times faster than Billy Hamilton, which is to say, light moves faster than the fastest player in baseball at a rate similar to how much more money Clayton Kershaw will make than an average GCL player this season. Einstein hypothesized correctly that no matter where light is, it will always move at this same speed, 186,000 miles per second, which is symbolized in science by the letter C. This led to the famous equation E equals mc squared, or energy equals mass multiplied by the speed of light squared. That the speed of light is constant, along with Einstein's assumption that all laws of physics apply to all observers relative to each other, led to Einstein's two theories of relativity. First, the special theory of relativity, and later, the general theory of relativity. The special theory of relativity says that time is related to, and thus cannot exist without, matter and space. Let's explain using our friend Steven. Prior to being traded to the Twins, Steven was in Seattle, pitching for the Mariners. When he gets on a plane from Seattle to Minnesota, he heads east at 300 miles per hour. But if Steven were to head towards Tennessee instead of Minnesota to pop in for a quick hello with the kiddos, the plane would go 300 miles per hour southeast instead of due east. The plane would now still be going 300 miles per hour, but it's only going about 212 miles per hour due east because some of its speed is being used to go south. Using this same graph, let's replace east with time and south with space. When Steven throws a pitch that moves faster and faster and faster in space towards the speed of light, the speed of time for the ants on board the ball starts to move slower and slower and slower. This relationship is called the space-time continuum. And Einstein decided that space and time were not two separate things, but instead one entity, space-time. Back to Einstein's bus now. Einstein realized that if the bus were to move at the speed of light, which is the absolute max speed for all particles in the universe as we currently understand it, time would stop. Theoretically, if we could move faster than the speed of light, we could go back in time, and this is the basis for theoretical time travel. In everyday human life, though, neither of these cases are really applicable. When fighter jet pilots fly at the speed of sound, which is about 900,000 times slower than the speed of light and air, which is why we see lightning before we hear thunder, and land their planes back at their aircraft carriers, they will have aged less than a nanosecond compared to their fellow servicemen who are standing at attention the entire time of the flight. Nonetheless, this phenomenon, known as time dilation, is measurable. When some astronauts come back to Earth after about 6 months in space orbiting at rapid speeds, their watches will be 3 or so seconds slower than the clock at Wrigley Field, due to time dilation, not because their clocks were slow. In addition to time dilation, at speeds near the speed of light, space also contracts. This is called length contraction, and it also contributes to the relativity of space-time. The special theory of relativity only applies to objects moving at a constant speed in a constant direction, but Einstein's general theory of relativity generalizes the special theory of relativity and Sir Isaac Newton's laws of gravity, and provides the conclusion that gravity is a geometric property of space-time, not some abstract pulling force. Large objects like the sun distort the space-time around themselves and create gravitational reactions. This concept is slightly more complicated than figuring out what field to be on every morning, but only by a little bit. The general theory of relativity is the basis for the assumed existence of black holes, and it explains the expanding nature of the universe. Einstein was a smart guy and all, and his theories of relativity were pretty neat, but he was still a nerd who couldn't handle Major League Heat. Now, from all of us here at Clubhouse Questions, we just like to say, we hope you liked this video, but if you don't like it, play better. Until next time, that Clubhouse question is going, gone.